Hello everyone, what's up? How's it going? My name is Aditya, and today we are going to discuss about D and F block elements. It is a very lengthy chapter, and we are going to cover it on a very surface level so that we can cover the important required concepts, and we'll talk about those concepts a bit. But again, it is advised that once the chapter has been discussed over here, kindly go and refer to the NCERT of this topic, okay? Because even though we have taken some tables from there over here for displaying purposes, but it would still be advised that you please go see those that chapter particularly again. So let's discuss about D block elements first, and then let's discuss about F block elements at ease, okay? So if I show you the periodic table over here, which is this, we have this section of elements, right? In this section of elements, we see that this a section of elements are known as our D block elements. And this D block elements actually, the thing is that over here, when we come towards 57 and 89, you see we get these. These are our F block elements. Okay. So our D and F block are located respectively on this and this particular point of at the periodic table. Another thing I would want to discuss is about the way in which the electrons enter into our orbital. So we know 1s, 2s, 2p, 3s, 3p, 3d, 4s, 4p, 4d, 4f, kind of the thing, right? And then we know that if it goes like this 1, 2s, 2p, 3s, 3p, 4s, 4p, like that it goes. Okay. So just keep this particular topic in mind and let us start D and F block elements. All right. So D block elements is basically general properties. Let's directly start off with the general properties of, yeah, I forgot to tell that these are called transition elements, okay? Because it is a transition from metallic characters to non-metallic characters. So there is a transition kind of a thing. That is why we call them transition metals, okay? And if we talk about an ionic and atomic radius, it is clearly and evidently visible that there is a subtle difference. Now, just another thing. This here is called the 3D series. This is called the 4D series. This is called the 5D series. And this is called the 6D series. Okay, so we have these four series that are present over there: 3D, 4D, 5D, and 6D. And the most important one again is our 3D series. Okay, because for every single thing that we are going to talk about, we will use the 3D and the 4D series. Okay, so quickly, let's just go to one of these slides that I want to talk about the 3D series that we will actually use to talk about the transition elements. Now, this picture has been taken from your NCERT. Okay, and hence we are just going to use this. Firstly, if you can see, okay, what happens is that we have a different oxidation stage. What happens is first it enters the 4s electrons and then it enters the 3d electrons, right? Because of the thing we told: 1s, 2s, 2p, 3s, 3p, 3d, 4s, 4p, and 4d. So it goes like this, then 2s, then 2p, 3s, then it goes on 4s, and then it goes in 3p, and then 3D. Okay, kind of like that. Okay. Anyhow, let's talk about that also slowly. But here is the thing. Notice that we have our enthalpy of atomization, and you can see it is increasing down the group. To some extent, it is increasing and then it again starts decreasing. Then it's increasing and then it's again decreasing. Right? So you see, it is in a very, how do I say, random way. And that is because if you notice the electronic configuration, this is fine. Okay. Then there is an electron increase. Okay, it should increase. It should increase. Then it suddenly decreased. And why is that? Because of the configuration. Just look at that configuration. Okay. Then again it decreases. Okay. Then again it increases. Then again it increases. These two are completely stable. Okay. So that is why you see the decrease over here. Or else again it starts increasing. Again it starts increasing. Again it starts increasing. Again it starts increasing. Then again the electronic configuration becomes stable. And that is why this thing becomes less again. Okay, so wherever you have a stable electronic configuration, you can see that it is comparatively low at that point. Okay, but it is not, or else it is generally in an increasing order. Ionization enthalpy, it's the same thing. Okay, the stable ones are very high. As you can see, this one corresponds directly to 717, and this one corresponds directly to 706. Or else, as we go down the group, ionization enthalpy is also increasing. Okay, now you can see that there are different ions that are possible. Now we are actually talking about 3D elements over here in particular. So you know that because they are even in your d orbital and they are even in your s orbit, d and s orbital. So you know that they can give their electrons, and which is the closest thing they'll go to? They'll go to the closest noble gas configuration of atomic number 18, which is basically neon. Okay, so neon, they will try to get a stable electronic configuration such as sorry, argon. 18 is argon and not neon. My bad, guys. So 18 is argon. They will try to get a stable electronic configuration as that of argon. And that is kind of what's happening over here also, as more and more ion is given. Okay. Similarly, you will get a corresponding ionization enthalpy. Like, let's clear the screen and show this part. If we see this, okay, if this loses this one electron, and then if we see in M plus, right? So M plus, the electronic configuration is 3d5, which is very stable. And that is why you see that compared to the next and previous and the next, it is actually higher than two of them. That is because this is stable, right? That is our second ionization enthalpy. How much energy you'll need to remove this particular electron, right? So that is how basically the whole trending of at all the enthalpies go on. All right, and let's just talk about the general other properties. We can see that at first we see a decrease in the atomic radius, and then it kind of like becomes constant, and then it starts increasing again. Okay, that is kind of like in this graph. Now in this graph, see, these are a 3D series. First, you can see the atomic number as it's increasing, it is metallic radius is decreasing. Okay. Then at a point, you see it is almost constant. Then again, it starts increasing. Okay. But if you see our 4D and our 5D series, their atomic radius graphs are almost kind of like overlapping on each other. And for this phenomenon, we have the like for this thing, we have the phenomenon called lanthanoid contraction, particularly that is responsible for this. Now, what is lanthanoid contraction? Now, if I again draw that graph, okay, so we draw that, we'll draw it here, draw it 1s, 2s, 2p, 3s. Okay, I drew it wrong here. 1s, 2s, 2p, 3s, 3p, 3d, 4s, 4p, 4d, 4d, 4f, and similarly, you have the other thing. Okay, so your 5d will come somewhere over here. Now, if it goes like this, we learned this in atomic structure, right? So you can see when we come over here, we are actually filling the 4F first, and then we are going on 5D, right? And this here, right here, is the reason for them having the similar atomic or metallic radiuses, because our 4F orbitals are filled before our 5D orbitals. Okay, and this creates a contraction in size. This thing is called lanthanoid contraction. Okay, and that is why we see the 4D and the 5D series exhibit similar radii. Okay, and because they have a very same atomic radius, they kind of like show the same physical and chemical properties also. Okay, then let's talk about enthalpies of atomization. Actually, we have already talked about it, how it actually increases, but then when a stable thing comes, it suddenly decreases. And similarly, it is the ionization enthalpy we talked about. Next, let's talk about the standard electrode potential. Now, the standard electrode potentials in itself is actually dependent on the ionization enthalpies. Okay, and if I show you the table over here, now they don't ask much of the standard electrode potential. That is also a thing because they generally give it in most of the questions. But if you see, when we have a stable one, it's generally negative. The standard electrode potential is negative. That means, look at this. Okay, let's see it like this. Let's talk about chromium. Okay, that means we are focusing on this particular column over here. Okay, let's just clear the text out. Okay, so we are focusing on chromium. Now, particularly, please focus on M2. Okay, or let's talk about manganese because M2 is stable over here. Okay, M2 is extra stable over here. And then we have M3, right? Now, if we wanted to go from M3 to M2, it will kind of like very readily do it, right? And that is technically why we have a positive standard electrode potential because it will readily want to reduce from M3 to M3 plus to M2 plus because we are achieving high stability in that case. Okay. Whereas if we want to see that would it want to go from M2 to M1? Probably not, right? Because it's stable and that would actually kind of like disturb the stability. That is what they are basically talking about this. The whole concept of ionization enthalpy, the enthalpy of atomization, and the standard electrode potentials kind of revolves around the electronic configuration part of it. So if we focus properly on the electronic configuration, then we can actually understand what is going on and how it is, and density gradually increases as we go down the group. Okay, and we have oxidation states. Now the transition elements actually tend to show a lot of different transition states, and again this particular table that is been featured over here is actually taken from NCERT, and the ones that are bold in color, right? The ones that are bold are actually the more common oxidation states of this thing. Right. So we see Cr plus 3 more commonly, then we see Fe plus 2 and Fe plus 3, but we don't see Fe plus 4 or Fe plus 6 that commonly, right? Similarly, we see zinc is always seen in a plus 2 form. Copper also we generally see it's a plus 2 form. Nickel also we have always seen Ni plus 2. Even when we were talking in coordination compounds, when you talk about it in coordination compounds, you see plus 2, right? So there you go. Like there are a lot of different possible oxidation states, and it more or less kind of depends on the stability, and again we fall back to electronic configurations for this, and that is kind of how the whole situation works. So this is a personal advice from my side that if you are trying to do D and F block elements, then kindly focus on the electronic configurations as much as you can. There are two, three reasons for it. Like the first one, see, like we just saw, if we kind of understand how the electronic configuration works, we can come to a lot of conclusions that we have to come to over here. And secondly, if you kind of remember the electronic configuration, it will be very easy for you to solve even complex compound questions, and if possible, even most of the magnetic moments question. That's kind of more like math, but yeah. Okay. So that those are like basic properties. Just keep lanthanoid contraction in mind. And now let's talk about magnetic properties and color formation. Okay, now we know magnetic properties. Any substance can either be paramagnetic or diamagnetic, as simple as that, right? It can be either paramagnetic or diamagnetic. And what does that mean? Paramagnetic means that they have unpaired electrons left, right? And diamagnetic means that they have paired electrons left. Well, we know that, right? Now, if we talk about a moment, like if we take a moment over here and talk about a thing called magnetic moment. Now, magnetic moment is actually a very important concept when it comes to D and F block elements. Okay. And even color formation is there, but we will discuss about this with ease. Okay. With ease. There is no pressure or rush over here. So, magnetic moment basically, we know that when our electrons spin, they are generating a bit of magnetism, and that is the whole ground story of it. But how do we calculate these magnetic moments, right? So we have the formula, that is n into n plus 1 and square root of it. This will give me mu, and mu is the general representation of magnetic moment. Okay, that's kind of clear. Now, what is n? N is the number of unpaired electrons, right? N is the number of unpaired electrons. Okay, so that is magnetic moment for you all. So what exactly, if anyone talks about magnetic moment, means that you need to first apply that formula, n into n plus 1 square root is actually mu. Mu is our magnetic moment, right? Now, we know that paramagnetic is when there are unpaired electrons present. And the formation of colored ion actually takes place because of the unpaired electrons that are present over there. Okay, so if our element is kind of paramagnetic in nature, then they will show us colors. Okay, now how does the color work? It's here that we use a concept called DD transition for the thing of colors in transition elements. Now we know this. Okay, we know this from complex compounds. Now what happens is, suppose, okay, we have an electron over here. Suppose. Now what happens is this electron gets some form of energy. Let us say some form of energy in the spectrum, right? So that absorbs that energy. What happens is that excites this electron, and this electron goes into a higher state, right? This much, are you there with me, friends? That we have an electron, the electron gets excited for some reason because of some energy or whatever changes you have made, and that electrons comes over here. Okay, now what happens is, now let's say when the thing has cooled down, that is, that excitement is gone, he'll realize that he's come way too far because of excitement, and he'll come back to his original place. So he will come back over here to his original place. Now, while coming back, he'll release energy, right? He'll release energy. Now, this energy or this radiation falls in the visible range. Okay, visible range. And that in basic, that is the color that we see of the compound. That is called a complementary color, but that overall is the color that we see for a compound. The color or the energy that has been radiated when it is de-exciting itself. That is, it is coming back to the original state it was, that it from where it went when it got excited. Okay, and because this is happening all within the d orbital, we call this whole thing to be a dd transition. That is what it is called, a dd transition. There is an other way, but a more commonly asked question type thing comes from the dd transition point of view, and hence dd transition has been discussed more in detail over here other than that. Okay, so I hope how you understood that how the DD transition kind of like works over here, and there how. the colors are coming out. Remember, the colors that we see are the complementary colors of the colors that are absorbed. Because see, energy is radiated, then it is absorbed, then something energy is radiated out. And these two are complementary of each other. Okay. So you can kind of like get the idea, right? If you find complementary colors, I mean, if you absorb one color, then you'll get a complementary color of the whole situation. Okay. Now, here is a thing, okay, that you have to remember. Firstly, let's talk a bit about complementary colors. Okay. Red has a complementary color of green. Red has a complementary color of green. Okay. Blue has a complementary color of orange. Complementary color of orange, and green has a complementary color of magenta. Okay. Green has a complementary color of magenta, or kind of like how it works, right? So like you got the concept of how it works. Okay, red gives green, blue gives orange, and if you like want yellow also, so yellow kind of like gives a purple. Okay, now you can get this complementary sheet kind of a thing from Google and everything. And yeah, so if our element or this compound absorbs energy that is from the red region of our spectrum, then probably the energy that is radiated out will fall around the green region of our spectrum. Okay, that is what it kind of means in a overall point of view. And how that happens is because of DD transition. Cool. Okay, I hope this much part of it is kind of like clear. And let's go over here. Next. Next page, if you see, actually, we are talked about magnetic moment and observed magnetic moment. Now, magnetic moment, that is BM or MM, that is easier to remember, is N into N plus 1, the root, right? Now, let's see scandium, Sc plus 3. How many unpaired electrons does it have? 0. So, what is the magnetic moment? 0. Cool. Now, if you see Ti plus 3, how many unpaired electrons are there? 1, right? 1 into 2. So that's 2. Root 2. Root 2 is around 1.732. 1.414, sorry. Right? Root 2 is 1.414. So that kind of like makes sense, right? Similarly, if you see 2 into 3, root 6 kind of a thing will happen. And that is kind of like how it goes on. Okay, the calculations of the magnetic moment. And yeah, so similarly, let's see the colors. Now you see there are no unpaired electrons present in Sc plus 3. That means it's completely diamagnetic. And that is why you see particularly Sc plus 3 is colorless. Ti plus 3, it has one unpaired electron. So you see here, Ti plus 3 has a purple color to it. Similarly, if we see zinc, it has no unpaired electrons. And over here, zinc is kind of colorless. Okay. So we can see a direct relation that is here between unpaired electrons and the D block element kind of like having a color or not having a color over here. Okay. So here we will write that thing that if our element has unpaired electrons, then it shows colors, or it shows its true colors, however you remember it. But this is kind of like how the whole situation works out. Okay. Now, formation of complex compounds is one of the most important things or properties that we have seen from our D block elements, right? We know that D block elements kind of have a tendency to form complex compounds, and we have seen this, right? We have seen a lot of complex compound having chromium or having iron or having nickel and everything sort of it. But why is the question? Now, see. we know that D blocks generally are empty most of the times, right? And that is a very important reason on why D block forms or complex compounds. Simply because when we talk about D block elements have unpaired empty orbitals, and it can accommodate it, and it can accommodate it in such a way that it results in the formation of complex compounds. Okay. Similarly, let's talk about the catalytic role, like how, a lot of D block elements, they have multiple oxidation states. And because they have multiple oxidation states, they can kind of like result in different type of catalytic properties, or can result in different types of complex formations to enable different properties, right? You can clearly know, you see, we have two different Fe plus 2 forms a different kind of an or complex compound, and Fe plus 3 forms a different kind of a complex compound, okay? So more or less, that is how it kind of works. And we have interstitial compounds, and basically what is interstitial compounds is you have big elements. Okay, and we have gaps in between big elements. So if uh which slide were we in? Yeah. So we have certain big elements. Let us say something like this. So what happens is when the small elements, okay, elements that have a small atomic radius come and fit in middle like this, or come and fit in middle like this. Okay, that kind of that kind of compounds are known as interstitial compounds. Okay, big when the small fits in between the bigs, that is basically interstitial compounds. And each of these interstitial compounds have its own unique kind of a property. And if you particularly want to know the structures and everything, then if you've understood solid states, then you have a basic idea what will interstitial compounds be. But these are overall what are interstitial compounds: compounds in which small metals or small non-metals fit in between the big metals. And again, a lot of alloys, different kinds of alloys are present over there, like brass or in, gunmetal and everything, where we use a lot of different transition elements. Okay. Now, the list of most of these alloys is done in a chapter called metallurgy. So remember that the list is kind of like given over there. Okay. And here is the thing. Okay. Now, we'll just some important transition elements we'll discuss about this. But now you can see that we have a pretty decent connections of different kinds of chapter. We have our D block, and that can actually be connected to our coordination compounds. It can actually be connected to our metallurgy, and it can actually even be connected to solid states, as we saw. It can be connected to a lot of chapters. So generally that we see when we talk about a very good question, we have very less direct questions coming from D block. Okay. Most of the time it's overall a very mixed kind of a question that is generally asked to us. Okay. Next, we'll discuss about two important compounds: potassium dichromate and potassium permanganate. Now, we know these two compounds very well thanks to our organic chemistry. Now, what happens in organic chemistry is simply that we know that these two are pretty good oxidizing agents present in organic chemistry. Now, potassium dichromate is actually having a dichromate ion, and even potassium permanganate actually has a permanganate ion. Okay. So put the dichromate ion kind of like a Cr2O7 2 minus. Okay, and this is how its structure is. You can see there is one bridging oxygen atom. Okay, and we are basically combining two CrO3s type of thing together. Okay, so we have a chromate ion and a chrome, like the oxygen becomes common between two chromate ions. That is why it is dichromate. You have two chromate ions. Okay, and a chromate ion is basically CrO4. Okay, And then you have the preparations, and the chemical reaction involves Na2CO3 and O2. And it is a strong oxidizing agent. It is used in volumetric analysis. Okay, this is basically our analytical chemistry part. Okay. Similarly, potassium permanganate is kind of made of the permanganate ion, which has a structure like this. Okay, permanganate ion. Now here is a color difference also. K2Cr2O7, that is potassium dichromate. If you see it at times, you will see that it is orange in color. And if you see KMNO4, then you see that it is purple in color. So there is a small difference in color also, and that color difference is basically what we use in our analytical chemistry, right? So yeah, these are two important, very important compounds that are present in our D block elements at over there. And along with these two, you have a lot of different compounds. But as this is discussed in the NCERT, and these are two very important compounds, these are discussed over here also. Okay. So keeping this much in mind, we can actually form pretty decent questions from D block elements. Now, this is basically here, if you see, we are done with D block. Okay. Now we have our F block elements. And F block elements is again divided into lanthanoids and actinoids. So if we go back over here to our periodic table that we have, these are our lanthanoids and our actinoids, or which we call the F orbital, F block elements. Right now, you will see this like many kind of similar things. If you have understood D block, most of the things in D block, F block is just like a kind of a copy paste of that whole thing. Okay. Why there you'll see a thing called actinoid contraction, and the same whole concept kind of like works over there also. So just keeping everything in mind that we have in D block, let us kind of like start from F block elements. Okay. So F block elements, which are lanthanoids and are actinoids particularly, and again they will try, they have the closest noble gas. If we see, they come over here. Okay, this whole table actually is here. Okay, and we see that the closest previous noble gas is xenon. So all these elements will actually try and get an electronic configuration that is close to xenon. Okay, and again, there are certain exceptions like we saw over there in our D block with zinc and chromium, particularly in the middle, that we have half filled orbitals and or fully filled orbitals of 4f orbitals over here that will actually give extra stability. And then there are a lot of irregularities also because of small energy level differences. Okay, because these are big kind of elements and they have a very small energy level difference among them. Okay, and now lanthanides have a common oxidation state of +3, and we have a lot of they can exhibit higher oxidation states also. And the thing is, comparatively, we see that lanthanoids show a very small range of oxidation states. If we see our D block elements going back, D block elements, you can see show a variety of oxidation states. Like if you see manganese, chromium, even nickel, right? To some extent, we have a variety of oxidation states, but that variety does not exist that much when it comes to our lanthanoids. And that simply is because there is a big or a significant energy gap between our 5D and our 4F subshells. Okay. Now, because of this significant energy gap that kind of like exists between the two orbitals, you see that there is a very limited range of oxidation states that takes place over here. Okay. Next, if we see, there are a few other properties like electrical conductivity, physical attributes, and its alloys with particularly iron, which we call as mish metals. Now, what are mish metals? Actually, the spelling of mish metals is MISCH and not MISH. HE. Remember, that is a mistake that I had basically done. And here is the thing, okay? Mish metals kind of like is 95% lanthanoids and 5% iron. Okay, even though like 95% of it lanthanoid, but it forms this alloy with iron that is known as mish metal. Now this can be like composition of a lot of things like cerium, lanthanum, or even neodymium. But there are a lot of this, okay? And where are like mish metals kind of used? The best example where mish metal is used are in bullets. Okay, so the most common place where you will find the use of mish metals is in bullets, gun bullets. All right. So remember this thing, this was a small thing about, mish metal, and also the physical attributes that they are silvery white soft metals that tarnish rapidly. Okay. Our F block elements are basically those. Now, again, we see, there is a diverse oxidation state, but comparatively less. And actinoids, if we particularly talk about actinoids, are again the smaller brothers of lanthanoids. And, they have a general electronic configuration. And you can see we actually go up to the seventh period, the last period over here, and they have a lot of oxidation state, whereas lanthanoids don't have that many different kinds of an oxidation state. And remember, these two can show colors, and the reason is kind of the same, okay? Because of how we saw it in B block element, that is our DD transition, okay? So DD transition is the same. Again, you have our color kind of a transition. Basically, there are two basic transitions, color related and DD transition. But as DD transition is a very, very important one compared to the other one, and it kind of like, you can get an easier knowledge and a more ask thing. That is why we have only discussed that again. Excuse me. And I'll again tell you that please refer to the NCERT once you have seen this, because this only contains like kind of, the headings and a very brief overview of what is kind of happening. Also, which would be the noble gas that, our actinoids would try to get closer to. So you see actinoids are from 90, meaning it'll be in this range over here. Okay, let me clear it. Our actinoids will come here. That means the previous closest noble gas is radon, Rn. So radon is the noble gas in which all of these dudes like thorium, uranium, neptunium, cerium, all of these kind of dudes. Sorry, that's not cerium, but yeah, you get the point, right? These dudes will try to get radon as their stable electronic configuration. And if we see comparison of actinoids and our lanthanoids, we have a thing called actinoid contraction, which kind of like leads to a gradual decrease in the size of our atoms and ions. And actinoid metal display a variety of structure, basically showing irregularities that are greater than that in lanthanoids. Okay. Also, before I end this, I would like to talk about a very small thing, and that is the reactivity. Now, reactivity. Okay, this is very same. Okay, we'll just talk about La. Okay, that's lanthanum. And we'll talk about their reactivities. Now, for lanthanoids and actinoids, okay, the reactivity is very much same to that of aluminium. Okay, how the reactivity happens in aluminium is exactly how you see the reactivity that will happen in case of these elements also. So now if I ask you that what will happen if I reacted with an OH atom, or what will happen that if I react it with, let's say maybe heat it, let's just heat it with oxygen or anything. Okay. So Ln, we talk about Ln later, and then La, kind of the same thing. So I'll just draw a basic graph that is there even in NCERT. Okay, we will say, let's say we have Ln in the middle. Okay, I'll make it red color. Okay, and we have our Ln. Now, if we react it with halogens, X, it will form LnX3, right? And what does aluminium form? AlX3, right? If we react it with water, what will this form? It will actually form LnOH twice, lanthanoids. Okay, all our Lns are lanthanoids. I just showed it with La, that is lanthanum ka example. But overall, this is the whole thing. Okay, this will give LnOH thrice. What does aluminium give? AlOH thrice. Okay, if we heat it with nitrogen, what will we get? Ln capital N. We'll get Aln, right? So you can see that the reactions of lanthanoids are actually very, very, very similar to that of our actinoids, sorry, to that of aluminium. And that is why it makes it very easy for us to remember our lanthanoids ka reactions, because you just need to remember what will happen with aluminium, and you know what happens with aluminium in that case, that is most probably what's going to happen over here with lanthanoids also. Okay, so that is like a whole kind of a thing on how the whole system works over here in F block elements. And remember that a few elements that are present here and there, they are like radioactive also. Like for example, if I say, let's go back to our periodic table, which is here, right? So we have a lot of different elements. Suppose this, you see promethium, PM, this dude, he's radioactive, okay? And he is the only radioactive material in this lanthanoids, okay? Where here, we have most of in F block, if we see actinoids, most of them are radioactive. And if you see properly, thorium, then you have protactinium, and you have uranium. Okay, thorium, protactinium, and uranium. These three, in fact, are naturally radioactive. That means you can find them in nature. Okay, so kind of you can remember this. I mean, it's a very small thing, but at times a good question would just become like, what is the only radioactive element that is present in your lanthanoids? And that is actually a promethium. Okay, if you keep that much in mind, I think it should work out pretty much fine. Okay, so now we just clear this because now we are going to solve questions. So this is your first question. Copper becomes green when it's exposed to moist air for a long period. Now, what is the reason? There is a formation of a layer of cupric oxide on the surface of copper, the formation of basic copper sulfate layer on the surface of the metal, the formation of the layer of cupric hydroxide on the surface of copper, and what happens, the last point, the formation of layer basic carbonate of copper. Okay. Now here is the situation. Okay. When you have a moist air present. Okay. Now what are the major components of air? You see, it has water, it has carbon dioxide, and it has oxygen. Right. What happens is copper kind of reacts with all three of them, and that kind of performs CuOH twice, and also it forms CuCO3. Now what happens is, because this carbonate is formed, okay, this carbonate is formed over here, it actually forms a layer kind of a thing over your copper. Okay, and that is what is happening over here. Copper reacts with your water that is present in the moisture, with the carbon dioxide that is present in the moisture, and with the, you know, oxygen that is present, and overall it forms copper hydroxide and CuCO3. Now CuCO3 is very is greenish in color. And if you don't know that, if you have seen the copper vessels that you see, or even leave that, if you have seen those copper bangles that a lot of guys wear, the tadas, that also becomes green after some time, when you wash your hands quite frequently, and when you just leave it like that, you see that slowly the brownish buffiness thing of copper eventually turns out to become green, and that is because of this. Okay, the formation of the carbonate over there kind of forms this, and that is what is the reason over here also. Okay, so if I remove this, okay, I should just do this. This is the reason copper becomes green when it's exposed to moisture for a long period because of the formation of a basic layer of carbonate of copper. That is this CuCO3 that is formed over here. So then what is the answer for this? This is option 4 is my answer. Okay. Next question. Iron exhibits +2 and +3 oxidation state. Which of the following statements are about iron is false? First one, ferrous compounds are most easily hydrolyzed than other corresponding ferric compound. Now, I hope you know what is the difference between ferrous and ferric. For those of you who are blank right now, ferrous refers to Fe plus 2 and ferric, we show it in a different color, refers to Fe plus 3. Okay, so this is ferric and ferrous. Okay, now coming to this, ferrous compounds are most easily hydrolyzed than the corresponding ferric compounds. Ferrous oxides are more basic than ferric oxide. Ferrous compounds are relatively more ionic than ferric compounds, and ferrous compounds are less volatile than the corresponding ferric compound. Now, if we know, let us see like this. Okay, ferrous oxide is what? FeO, and ferric oxide is what? Fe2O3. FeO is more basic than Fe2O3. Okay, and FeO is also less volatile. Okay, but what happens is when we see, we'll do it like this. Okay, so we know that this is we didn't talk about this, but this is correct, and volatile, this is correct, right? These are like facts kind of a thing. I mean, it's more of the table. If you understand the table and how it is, then you will kind of like get an idea of what it is. Again, it falls down to the electronic configuration. And similarly, Fe plus 2 ions are more, Fe plus 2 L compounds are more ionic and kind of like makes sense, relatively more ionic than this. So we clearly saw that, you know, our option 2, option 3 and option 4, ye teen to, I mean these three are coming correct, right? And because these three are coming correct at this point of like at this point, we can clearly and directly say that our first one is wrong. Okay, so you can refer to this table that is actually shared in the slides over here, this one, to get an idea of what is why Fe plus 2 is more basic than Fe plus 3. Now, basically, why is it more basic? You will get to know it over here. And why is it more, which is more acidic? You will get to know it, understanding the electronic configurations that are over there. Okay, let's come to the next question. I mean, let's go back to the slide first. The lanthanide contraction is responsible for what? Okay, now we have two things. Okay, we have ZR and YB and ZR and HF and ZR and NB and ZR and ZN. Okay, so basically we know that our 4D and 5D and 4D elements have a very similar kind of thing. Okay, and here are the pairs. Like you can see it, we have actually paired it over here only. LA and Y kind of are a pair. ZR and HR, HF actually, this should be HF. HF kind of have a same pair, ZR and HF. You have Na and TA and NB, and you have MO and W actually. MO and W. So there are a lot of things. Okay. Now coming to the question, we are actually talking about ZR and HF. Okay. And ZR and HF are pretty close to each other when it comes to, you know, what is happening and how it's happening. So yeah, that is how the whole thing is dividing into. So in this case, if we see this question properly again, our answer will be ZR and HF. That is option 3. And then these are the pairs that are HF, MO and W, Na and TB. They have the same chemical properties because of a thing called lanthanoid contraction and blah 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 blah. So option 3 is the answer over here. Okay. So next question. Knowing that the chemistry of lanthanoids is dominated by its +3 oxidation state. Here is the thing. Because it is dominated by the +3 oxidation state, it is very similar to aluminium. And that is what is that point we discussed over there, that we told that they have a lot of similarities. That is basically because the +3 is a more common oxidation state. Basically, it's dominated. Okay. Now these are, the basic compounds kind of things you can say. So firstly, we have to tell which of the statements are incorrect. Okay, first statement, because of the large size of the Ln+3 ions, the bonding of its compounds is predominantly ionic in character. Is that correct? Are most of our aluminium things ionic? Yes, it is. So this is correct. Okay, ionic sizes decrease with the increase in the atomic number. Yes. Okay. Ln3 compounds are generally colorless. Now we know that color or colorless kind of depends on whether it will have empty orbitals or not, right? If it will have empty electronic, basically non-bonded ones, right? If it's paramagnetic, non-bonded electrons, that time it will basically have no color. Okay, but if we observe our tables that are given in NCERT, and I forgot to put the slides, but yeah, NCERT is actually open right here in front of me. So in NCERT on page 236 of part 1 wala book, in second year one, you will see that there are actually, they have unpaired electrons present in them. And that is why our Ln compounds actually are not colorless, right? So option 3 is the answer over here. And if you want to see the reason, here's the reason. Let me just clear the slide. Ln compounds are usually colored in the solid state in this because there is a presence of unpaired F electrons. So it FF transition, right? Like we told, they have unpaired electrons, and hence FF transition is possible over here, and that is basically what results in its color formation. Okay, this is a very, very, like a kind of an example that has been combined with its central atom, like with a bit of like complex compounds. Now, what we have is we have a complex compound, right? And we have different kinds of our central metal atoms. So in this case, we have copper, we have nickel, we have Ti, and we have Co. Right. Now, if you actually know how to calculate it, you will know that this is Cu plus 2. Okay. This is Cu plus 2. This is Ni plus 2. This is Ti plus 4. And Co is in, so the minus 6. This Co is in plus 2. How did I calculate? Let's just say copper. We take this. So copper, we are telling it's X. Okay. Then we are finding NH3, that is 4 of them are there, but they are 0, so there's no point. So this is plus 2. So what is the X coming? X is coming plus 2. I hope you know this, okay? So this is what is there. Now if we go to our table, that is here. Okay. So you can see Cu plus 2 is there. Mn plus 2 is there. Ti plus 4 has 0 unpaired electrons. So we can see that here. Right. So from this, actually, you can calculate all of the you can calculate the oxidation states that are basically there, right? Or so like what I was trying to tell is this has one unpaired electron first conclusion. This has two unpaired electrons. Ti plus 4 has 0 and Co plus 2 has three unpaired electrons. So you got the number of unpaired electrons. Now you have two ways. Either see this, which is coming closer to 1.73, right? Or you perform it the other way around. How you will get? Now if you solve this, okay, your correct answer will actually come out to be n into 1. N. Sorry. Okay, so yeah, my mistake here. when we talked about magnetic moments, it is actually n into n plus 2. Where is it? Here, right? It's n plus 2 and not n plus 1. My sincere apologies. Okay. And keep that in mind that it's n plus 2, and that's basically how your question will be solved. So, this is the whole solution for that, that it is n into n plus 2. Again, that is the formula. You can solve n equal to 1 and then do this, or you can do it the other way around, the reverse psychology kind of a thing. Okay, so that completes D and F block. And please revise the NCERT ones on how to do and what to do. And these were most of the important topics that were present over there, and they have been discussed with you over here. Okay. So thank you everybody for listening, and we'll see you in the next class. Okay. Thank you. Bye bye.